Welcome everyone to our fourth lecture. So last time we saw the concept of a submodule when a module is decomposable if it has a non-trivial submodule, and we defined also the complement of a submodule when you're able to find another vector space that's also a submodule, such that the original module V is a direct sum of those two submodules. So we were we were discussing ways to find a complement of a submodule. So one way to do it is using an inner product. So if say that V is a vector space with an inner product, we say that it is invariant under the action of the group if the inner product of GV and GW is the same as the inner product of V and W for all elements of the group and U and V. And if we have such an inner product, we define the complement or the complement of W perp to be the elements in V that are orthogonal to all the elements of W. And from linear algebra, if we have an orthogonal complement, then the submodule is direct sum. The vector space is the direct sum of W and its orthogonal complement. Okay, but the benefit is that if we have a G module and we have an inner product that's invariant under the action, then the orthogonal complement with respect to that inner product is a G submodule. And let's remember how we use that. So we had the example of the defining representation, and we had a one-dimensional submodule, the span of the sum of the vectors 1, 2, and 3, and we wanted to find the submodule. So we can define an inner product that we define it on the basis. So it's the inner product that takes the vectors I and j to the Kronecker delta ij. So 1 if they're both equal and 0 otherwise. That's this Kronecker delta. Okay, and remember that this is, and then we extend it, but remember this is a complex inner product. So we need to take complex conjugate on the second coordinate. Okay, and this inner product is G invariant. It's invariant under the action of the symmetric group, because if we're going to take the inner product of pi I and pi j, we get the Kronecker delta of pi I pi j, but pi is a bijection, so pi I and pi j are the same or different if and only if I and j are the same or different, because pi is a bijection. Okay, so it's Sn invariant. So therefore, the orthogonal complement of the span of, this should be of the vector 1 plus 2 plus 3, so W, is going to be a submodule, and then we just find, so in this case it's going to be a two-dimensional space, and I just pick a basis that's orthogonal to 1 plus 2 plus 3, okay? And then I know that if I call this U, then I'm going to have that V is the direct sum of W and U, okay? And then in terms of the associated matrix, means that if I pick a basis of V that is a basis of W and a basis of U, then the associated matrix is going to have this block form. So where the only non-trivial blocks are in the diagonal. Okay, so in this case it would be this 1 by 1 block and this 2 by 2 block. Okay, in this particular case, because one block is one-dimensional, it's irreducible, and in fact this 2 by 2 block also happens to be irreducible, but we'll see that later. Okay, so let's take this idea of finding a complement and use it for any representation. So we ended up stating this result, that if we have a finite group, so we're here in the bottom, and V is a non-zero G module, then V can be written as a direct sum of irreducible G submodules. Okay, so we stayed there, and the goal today is to prove this result, give some corollaries, and then move on to the next topic, which is going to be G homomorphisms. Okay. Okay, so we're done with the review. Okay. And so today we will prove Maschke's theorem, and we will talk about G homomorphisms. And we'll talk about G homomorphisms and a second result called Schur's lemma. Okay, so so here is Maschke's theorem. So what is the matrix form of this result? So if we have V is a d-dimensional representation, G module, then there is a basis such that the associated matrix xg has a diagonal form. So I can write it in this diagonal form. So the rest is 0, where each xig is an irreducible matrix representation. Okay, so that's equivalent to Maschke's theorem. That's what we get from for the matrix representation. Okay. But we want to give a proof of this result. Okay. So let's go ahead. So we're going to proceed by induction on the dimension of V. Okay. So if D equals 1, that's our base case, then V is irreducible, and we're done. Okay. So now if D is bigger than 1, again, if V is irreducible, we're done. So let's assume that V is reducible. Okay, so V has a non-trivial submodule W. Okay, so the induction would apply to W, and because it has dimensions smaller than D, so we can decompose it into irreducibles by induction. But we want to decompose not just W, but the whole of V. Okay, so our strategy is going to build a complement of W, and then decompose both W and the complement of W by induction, and then we will be done. Okay, so we need to build a complement of W. Okay, and we want to use our proposition that we can do so if we have a G invariant inner product. So we need a G invariant inner product. Okay, so let's define an inner product I should have first pick a basis of V. Okay, and I define an inner product defined by so something similar that I did for this for the example of the defining representation, by being the Kronecker delta dij's. Okay, so if vi and vj are the same, 1, otherwise 0. Okay, but this is not necessarily G invariant. Okay, so let's discuss why. So, well, if I take an element in the group, GVI is going to be a linear combination of the vectors in the basis v1 up to vd, but not necessarily a single other one, a single other element in the basis. I'm not necessarily a permutation representation. Okay, so I really don't know. I cannot guarantee that this is going to be an invariant inner product. So so I need to define a new inner product based on this inner product that will be G invariant. Okay, so I'm going to call that the inner product prime. So, and I'm going to define it by kind of averaging out over the whole group. Averaging it out over the whole with the other inner product over the whole group. So what do I mean by that? So I'm going to say that the inner product of vi and vj of this new inner product, I'm going to define that to be the sum over all the elements in the group, and then g applied to both vi and vj, but where I'm adding over the first inner product. So this is, so maybe I should put some colors here. So I'm using this inner product, I'm reusing it here in this sum. Okay, so I should call this one kind of red. Okay. Okay, so I'm just having a little bit of fun here with the colors. Okay. Okay, so here's a definition. So let me get rid of this. Okay, so we get rid of this. So I have the induction here, the proof, sorry. So the claim is that this new inner product is G invariant. Okay, so let's see that. So let's take an element in the group. Okay, so then the inner product of h vi h vj. So by definition, this is going to be the sum over the elements in the group. Oh, this is the first inner product. It's going to be the sum. I should probably just use black here. So this is the inner product. This is the sum of, it's going to be GHVI, GHVJ, but I'm summing over the whole group. So that's the same. So H is fixed, and I'm adding over G times H. So that's, as I sum over, as G goes over the group, I just go over the group. So this is equal to the sum over the group of GVI, GVJ. And this is precisely the original inner product, so the second inner product at VI and VJ. Okay? So I was able to construct a G invariant inner product. Okay, this one with prime in the one that's red. Okay. So then, recall the proposition here. If I have a G invariant inner product, then the orthogonal complement of a submodule is also going to be a submodule. Okay. So continuing with the proof. So continuing with the proof, since is G invariant, then by proposition 1, the orthogonal complement of W is a G submodule. Okay, so where am I? Well, so then I have that the original module V is the direct sum of the non-trivial submodule and the orthogonal complement of this submodule, which is also a submodule. And then by induction, W decomposes into a direct sum of irreducibles. Okay, where Wi are irreducible submodules. And also by induction, the complement decomposes into a bunch of irreducibles. So let me call this K minus L. Okay, so together, V decomposes as a direct sum of irreducibles. Okay, the ones from W and the ones from W perp. Okay. Okay, and both the W's and the Wi's and the Ui's are irreducible. Okay. Okay, so and this finishes the proof. Okay. Okay. So let's pay a little bit closer attention to the assumptions here of Matschke's theorem. So it says that the group has to be finite. So where did we use that? Well, we used it in the definition of the new inner product, because we summed over all the elements in the group. So this sum better be finite. So we use that there. But do we need that assumption so that the result is true? I mean, we use it in the proof, but it doesn't mean that necessarily we need this assumption. So let me mention that again. So let me make a remark that the field C can be replaced by another field of characteristic 0 or of characteristic 0 or a characteristic that's relatively prime to the order of the group. Okay, and so if this is the case, the theorem still holds. Okay, but the assumption that the group is finite is essential. Okay, so let us give a famous counterexample. So I need to work on an infinite group. So I'm going to take G to be the reals, the positive reals, with multiplication. Okay, and I claim that if R is a positive real number, then this is the following is a two-dimensional matrix representation. So I have an upper triangular matrix, and I have log of my real number R. Okay, so this is you can check that this is a degree 2 representation. Okay, and if Maschke's theorem applied, that means that I could write so if it applies, it means that I can find a basis that that writes this matrix representation as a block matrix of just diagonal blocks. But since this is degree 2, those blocks and those blocks are irreducible. Those blocks have to be of 1 by 1. So it means that it means that basically I can diagonalize the matrix. So if XR can be written as the direct sum of 2 irreducible representations, well then the dimension of each of these ones would be 1. So what does that mean? That would mean that so that would mean that there is a basis So that would mean that there is a basis. So that would mean that there is a basis. There exists 2 by 2 invertible matrix T that diagonalizes XR for all R. Okay. But the contradiction is that XR is not diagonalizable for all R. Okay. So in particular, so the only possible eigenvalues of this upper triangular matrix are 1, okay? But this matrix actually is not diagonalizable for all R. Okay, so that's the contradiction. Okay, so Maschke's theorem does need the assumption that the group is finite. Okay. Okay, so this finishes. So this finishes the subject of reducibility for now. So now we're going to talk about G homomorphisms. I think we're in 1.4. So now we're going to talk about G homomorphisms. Okay. So we've talked about modules, submodules. So now we're going to talk about maps that go from one module to another. So if we have two modules of the same group, G modules V and U, then we say that a G homomorphism is a linear transformation theta from V to U that kind of preserves the action of G on both V and U, such that for all G in the group and V in V, we have that G of theta V is the same as theta of GV. Okay. So let's look at a couple of examples to get acquainted with this, to get familiarized with this. So if we have, so V is going to be the span of just one vector, and G is going to be Sn, and Sn acts trivially on V, so that means that pi of V equals V for all pi in Sn. Okay, so that's the basis of my vector space. So that's one of my representations, and the other one is the defining representation. Okay, where this and the symmetric group acts here on U. So this is also an Sn module, and I'm going to define a map from V to U, a linear map, and it's enough if I define it for the basis. So it's going to send V to the sum of the vectors. Okay, so this is an Sn homomorphism, since, so let's see why it is. So if I have a permutation in Sn, if I have, let's see what this is. So theta takes V to the sum of the vectors 1 plus 2 plus ... And then we've seen before that pi, the permutation pi, just fixes this vector. Okay, that's on the one hand. But now if we take V and we permute it, and we act on pi, and then we take theta, what do we get? Well, the symmetric group acts trivially on V, so this is just going to be theta V, and theta is just this sum. Okay, so in both ways, this way here and this way here, we obtain the same answer, so they're equal. Okay, and that's what it means to be a G homomorphism. Okay, so that's an example of a G homomorphism. Let's look at another example. Okay, so here V is again going to be a one-dimensional representation. G is still going to be the symmetric group, but then the action of a permutation pi on the vector V is going to be, we're going to get a multiple of V, but it's going to be scaled by plus or minus 1 depending on the sign of pi. Okay, so that's also this is also so this is a representation. This is a Sn module. Okay, and now U is going to be the group algebra. Okay, so remember what this is. This is the set. This is the set of the sums of permutations with complex coefficients. Okay, with the usual action of the symmetric group. Okay, so we define this this submodule. Okay, and now I'm going to define another linear map. So it's going to be from V to U, and it's enough if I specify what's doing to the basis. So theta of V now is going to be the sum over all permutations, and they're going to be scaled by the sign of pi. So the coefficient, so I'm going to just take the sum of the permutations and then the coefficients of each permutation is its sign. Okay? So that's enough to define a linear map, and this is also an Sn homomorphism. Okay, and I'll let you check this as an exercise. Okay? Okay, so here are two examples of G homomorphisms. Right? Okay, good. So let's move on. Okay, so if I have a G homomorphism that's one-to-one and onto, that's going to be called a G, an isomorphism. Okay, so we have two G modules V and U. So we say that V is isomorphic to U, and we write V isomorphic to U if there is a G homomorphism theta from V to U that is one-to-one and onto. Okay, so it's an invertible linear transformation that also happens to be a G homomorphism. Okay. Okay, so you know, this should be very similar to when you studied linear algebra, kind of the structures we're encountering. Okay, so so let's look at an example of this. So it's kind of an example we left a little bit in the air before. So we had seen an example of a left coset representation. So we had seen, so our group was the symmetric group with 3 elements. H was a subgroup consisting of the identity and the transposition 2 goes to 3. Okay, and we had these cosets. Okay, so these are the these are representatives of the cosets. I mean, the subgroup has size 2, so the quotient group has size 3, so there are 3 cosets, and they have an action of S3, a left action. So you know, so pi, you know, just so let's remember that if I have a coset G1H and I act on a permutation, it's just going to be, I multiply these permutations and I see what coset they belong to. Okay, and for this example in S3, we calculated, we took, for example, I think the cycle 1, 2, and 3, and we calculated the matrix corresponding to that cycle, and we saw how it acted on the cosets, and we found that it was this matrix, and this coincided with the permutation matrix of this 3 cycle. So it coincided with the with again the defining representation. Okay, so that was kind of puzzling. So let's try to answer this using this notion of isomorphism. Okay, we continue with this example. So we have this left coset representation, and we have an example of the symmetric group with 3 elements. We have this subgroup with 2 elements, the identity and the transposition 2, 3. There's 3 cosets, H, the left coset of the transposition 1, 2, and H, and the transposition 1, 3, and H. And we have this action of S3. And it seems, just by doing this one example, that we obtain the same matrix as the defining representation. So we're going to show that this left coset representation for this subgroup is isomorphic to the defining representation. Okay, so to see this, recall that this subgroup is isomorphic to a direct product of symmetric groups. So we're fixing the identity and we are permuting 2 and 3. So this subgroup here is isomorphic as groups to the symmetric group acting on one element, and the symmetric group acting on 2 and 3. So a convenient way that we will see later of representing the direct product of symmetric groups is something called a Young tabloid. So this is an array of integers of a shape of a partition. So this is an integer partition. Okay, and we put lambda 1 integers in the first row, lambda 2 integers in the second row, and they're kind of left justified. Okay, so let me do an example. So for so an example could be if I have 1, 1, 3, 1, 2, 4, and 5. Okay, so this has shape. There's 4 integers in the first row, 2 integers in the second row, and 1 integer in the third row. And the order within the rows does not matter. So this is the same as if I, for example, swap the first one with a 3. And if I swap, say, the 4 and 2. Because the order in rows does not matter. Okay? So, so for example, if I have a shape to 1, and the integers 1, 2, and 3, then I can have the tabloids 2, 3, 1. I can have the tabloid 2, 1, 3, and 3, 1, 2. Okay, so I have my shape is 2, 1, and I have the integers 1, 2, and 3. Okay, and these are the 3 possibilities. So which of these 3 looks like my subgroup H? Well, it seems that it's the first one because I am the direct product of S1 and permuting 2 and 3. So here on the first row I have 2 and 3, and on the second row I have 1. So this first tabloid looks like H. Okay. Now tabloids have a natural action of the symmetric group. So if I have a tabloid, if I have a permutation pi, and I have a tabloid I1, I2, I lambda 1, dot dot dot. Okay, so this is a tabloid. So the permutation would just act on the individual integers. Okay, so this would be pi I lambda 1, and pi would continue acting in all the rows. Okay. Okay, so for example, if I have this tabloid here, okay, and I act on permutation 1, the transposition 1, 2, well, 2 is going to go to 1, 3 is going to stay fixed, and this is going to go to 2. Okay, and this looks like, so this outcome here looks like the coset 1 to H. Okay, and now if I let 1,3 act on this tabloid, I'm going to get 2 stays put, 3 goes to 1, and 1 goes to 3. And this is the same as the tabloid 1, 2, 3. Okay, and this looks like the coset 1, 3H. Okay, so let me continue this here. So the symmetric group acts on these tabloids, so I can define a representation out of this. So I can take these tabloids and make a basis. Okay. Okay, and let the symmetric group act on these. Okay, so this is a representation. Okay, and now I can define a linear transformation between V and this representation of the cosets. Okay, and it's defined exactly in this way. So I send. Oh, I guess I should. Yeah, maybe I should. Yeah, just to be consistent, I should swap the role of V and CH here. Okay. So the way I define it is I send H to this tabloid. I send this coset. I should copy this. Oops. Or just, good old rewriting. So okay. So I define it as H goes to this tabloid. This coset goes to 1, 3, 2. Okay, and 1, 3H goes to the tabloid 1, 2, 3. Okay, so this defines a linear transformation if I just extend it because I define it on the basis, and you can check that this is an isomorphism. Okay. Okay, so it seems like I'm kind of taking a very long way to show that this left coset representation is the defining representation. So let's see where we are. Okay, so we have shown that this coset representation is isomorphic. Well, you have to check some things, but it's isomorphic to the representation of these tabloid. Okay, but now I claim that this representation is isomorphic to the defining representation, and oh, I think this should be 2, 3, 1 here. So the way to do that is, well, if you look at these tabloids, they have shape 2, 2, 1, 2 elements in the first row and 1 element in the second row. So they're uniquely defined by what I have on the second row, the single element on the second row, because I need to use the letters 1, 2, and 3. So this, in turn, is isomorphic to just these bottom entries. Okay? And this is the defining representation. Okay, so that kind of explains why we saw that. Okay. Okay, so that finishes this example of an isomorphism. Okay, so let's finish up with one more result. So if we have G modules U and V, and we have a G homomorphism from U to V, okay, so recall that the kernel of theta are the elements of U that get mapped to 0. Yeah, I think I swapped the orders of V and U, so this should be V and U to be consistent with the beginning of the class. So the kernel are the elements of V that get mapped to 0. Okay, and this is a subgroup of V, and the image or range of theta are the elements in U of the form the image of V under theta. Okay, and this is a subgroup of U. Okay, so if you have a G module and you have a G homomorphism, okay, then the kernel of theta is a submodule of V, and the image of theta is a submodule of U. Okay, so if we have a G homomorphism, we obtain two submodules: the kernel, which is a submodule of V, and the image, which is a submodule of U. Okay. So if we ever have a G module between irreducible modules V and U, well, they're going to be restricted because well, that imposes, since the irreducibility of V and U imposes restrictions on the kernel and the image. So that's the content of our second main theorem, called Schur's lemma. So the same Schur we're going to see when we study symmetric functions, the Schur functions. So what do we have here? So if we have that V and U are irreducible G modules, and we have a G homomorphism V to U, then two things can happen. Then either theta is an isomorphism, or it is the zero map. Okay. Okay, so let's think about the proof of this. So the proof is quite short. Well, V is irreducible, and the kernel is a submodule. So either the kernel is 0, well, either the So the kernel has to be trivial. So either the kernel is 0, which means that, so this means that my map theta is 1 to 1, or the kernel of theta is the whole of V. And in this case, well, theta is the 0 map. If I'm in the first situation where the kernel is 0, so then theta is 1 to 1, well, then since U is irreducible, and the image is a submodule of U, well, then the image is also trivial, but it cannot be 0 because the kernel is not the whole of V. So then the image of theta equals U, which means that theta is also onto. Okay? So now theta is 1 to 1 and onto, so theta is an isomorphism. Okay? And that finishes the proof. Okay? So next time we're going to see some formulations and corollaries of Schur's lemma, say for matrix representations and commuting matrices.